Hi, and welcome to Lecture 13, the first module of Lecture 13, which is the first lecture in the last part of this course, Part 5. This part of the course covers multivariable calculus and is, in many ways, the most difficult part of this course. That said, this particular lecture is not the most difficult part of the course necessarily, and that's because, unlike all previous lectures, which mapped pretty well onto chapters of the textbook, this one actually takes the chapter of the textbook, chapter 15, and splits it into two separate lectures. And the reason is some of the stuff in this chapter is more difficult, requires sort of more understanding of linear algebra, of all the prior parts of this class, and is really a capstone to this course. That's stuff we're going to talk about in lecture 14, the next lecture. Some stuff in this chapter, in chapter 15 in the book, however, is more general, is more stuff that you would need to know and really benefit from knowing earlier on. So even if you decide not to go on to the rest of this part of the course, to the lectures 14, 15, and 16, it's important anyway to still do this particular lecture because it covers some topics of importance that are really relevant to you as just a general practicing political scientist or social scientist. And these topics are, one, functions of multiple variables, right? Multivariable functions. These come up all the time. We'll give some examples in this module. This topic of this module is multivariable functions. Two, which is the topic of the second module, is partial derivatives, and there partial derivatives and conceptualization of partial derivatives are central to understanding things like regression analysis and basic game theory, and there we'll talk about that in the next module. You've already seen a little bit of that when we did calculus. We talked about partial derivatives a little bit. We'll do a little more now with a little more formalism. And the third part is on multi-dimensional integrals. That might seem scary, but again, it just means an integral done one time in a row in practice. And this is useful for understanding probability in more than one dimension, so it comes up a lot as well. So there's these three modules, and this lecture is only three modules. These three modules are things that I believe are pretty useful for all practicing social scientists, and therefore are worth going through even if you're not going to go on to the more difficult material at the end of the course. So I've taken this stuff and split it off to have its own lecture that covers stuff that's more general, that's more useful to a wider group of people. Not that the stuff coming after this is not also useful, but it's a little more specialized and a little harder, and it's stuff that you can reasonably go back to after a first course on mathematics. That all said, let's get to the topic of this particular module, which is functions of multiple variables. If you recall, way back when we first talked about functions, we defined functions in this way. A function of x, the variable x, the argument of the function x, maps, because a function is a mapping, some set A, which is the domain, the elements of the set A are the domain of the function, to the codomain B, and here the important part of the codomain was the range of the function, which is the set of all values that the values in the domain map to by the function. So the function takes some, say, subset of the real line, -1 to 1, and then maybe those elements of the domain end up getting mapped to anything from 0 to infinity. Well, there's the range of the function and here, domain and range. So that's what we talked about before. Now, what changes when you have more than one variable? The simple answer is not much. So now, let's start making a first step by changing that x and make it into a vector. Recall vectors we talked about in linear algebra. If you did not go through that part yet for some reason, and you really should have gone through that part before you get here, but if you have not, a vector just contains a bunch of elements. So this vector x here contains, say, elements 1, 2, and 3, x1, x2, and x3, and that's a column vector. So basically, this is the same thing as writing it's a function of three components, x1, x2, and x3. Now this does is it takes that those three arguments, those three components, those three variables, and maps them into some outcome. In this particular case, since I have not drawn f as a vector, that means f is a scalar, which means it maps these three variables into a single variable. So that's one possible function. a slightly more complicated version would have f be a function as well. I'm sorry, a vector as well. So this thing might map some elements of the set A, now A is in more than one dimension, into some elements of set B, which is also in more than one dimension. What does that mean practically? Well, that means f is a vector, so you could write f like that, as, say, some components. Let's make 4 this time. Now f is also a vector. How do you deal with that? Well, let's say x is a component, has 3 components, and f has 4 components. You could actually write the whole thing out like this. I think I've committed myself to doing that right now. x2, x3, and x1, x2, x3. There you go. This is the full way of writing out the entire vector f. Note that all you're really doing here is having more stuff, right? So before f was a function of a single variable x, now f is a function of 3 variables, x1, x2, and x3. Before the output of f was just a single scalar, now the output is actually 3 components, f1, f2, and f3, and f4, sorry, 4 components, and that makes a vector f. Together you have a multidimensional domain and a multidimensional range. Typically, A and B can be anything, any subset of some multidimensional sets. Typically, A is going to equal some, people often say the real numbers, and B is going to equal the real numbers to the n. Here, remember, this is the symbol for the real numbers. The superscript means we're in an m-dimensional space, so it's the real numbers attached to the real numbers again and again and again, m times, and the domain has n times. Here, m, in our example, would be 3, and n would be 4. And all this means is you have the input is 3-dimensional, right? They're elements of 3-dimensional space. The first dimension is x1, the second dimension is x2, the third dimension is x3, and each one of those x's comes from the real numbers. And here n is 4 means the first element of the range is going to be f1, and then f2, f3, and f4, and each one of those components comes from the real numbers. That's sort of the general way of writing a function in multiple dimensions. Let's give a couple of examples with actual things here. Let's do a little simpler one. There's some more complicated ones in the book, but let's just say you have a function of 2 variables to start off with. Well, what is that? That could be x1, x2. That could be x1 squared plus 2x2. That could be x1 times x1 minus x1 to the x2. Or that could be to x2. You don't have to include all the variables that you have a function of in the actual function. The important part is it could be a function of more than one variable. And again, you can add constants to these things too, right? It doesn't matter, like 7, whatever. So here are variables. If I wanted to do more than one, a vector f, well, I'll just define them separately. So let's do this one. Let's have a vector 2 components. Well, here's my my vector f. Well, let's say this one could be x1, x2 times x1 to the x2 minus log of x3. Another one. And let's say this one could be x1 squared minus x3 squared. Again, note that every component does not need to include everything it's a function of. The point is it could be a function of all these different variables, and you just define each component of f separately. So really, even though you now have more than one variable, and potentially more than one component of f, it's really just bookkeeping, right? It's more stuff that's thrown in there. Instead of having, say, a single function like this, x squared, 7x squared plus 2x minus 1, you replace the 7 with x2, the x with x1, and let's say the 2 with x3, and maybe the 1 with x4, and suddenly you have a function of 4 variables, right? You just change the constants to having more variables, but fundamentally you're doing nothing differently. You're basically you're evaluating the function at a particular point. In this case over here, the point is x. In this case over here, it's the point x vector, which is equal to the column vector x1, x2, x3, x4. So it's a point in four-dimensional space, but it's still a point. You're evaluating the function at a point. If you have a function of more than one component, so it's a vector valued, it's called a vector valued function. So these things over here, there's an f, that's called a vector valued function. But all you're doing is evaluating each component of f separately, and then sticking them together into a vector. So it's really as much bookkeeping as anything else at this stage. Okay. Let's take a step back for a moment and just ask some questions, like why would we do this? Well, you might guess that in real life, right, the things we care about, why people vote, why are there wars, right? All these big questions probably depend on more than a single variable, right? You can't explain voting behavior based on a single variable, no matter how great that variable is, right? You can't explain Civil War onset by a single variable. So in practice, we need more than one, and usually many variables to explain our outcome, right? Many explanatory variables. And once you have many explanatory variables, formalizing the interaction you're talking about here, formalizing the outcome, say the chance of war onset or the chance of voting, is going to end up being a function, is going to end up using a function of more than one variable. So if I care about, say, the probability of voting, well, then this might be a function of, say, education, and let's say income, and maybe social class, and maybe region, and maybe location, and so on and so forth. These are all different variables that are input into your function to give you a prediction for some probability of voting. So therefore, your function is a function of more than one variable. So that's why and this is true for pretty much everything we do. Why might you have more than one component for your function itself? Well, maybe you have linked outcomes. Right? We talked a little bit about how to solve systems of equations in the previous part of the class. Right? Well, more than a little bit, I guess. We talked about how to solve systems of linear equations. And we discussed how that was sometimes useful for doing game theory problems. If you have two actors, you want to simultaneously solve their equilibrium actions. Well, you might have the strategy of player 1 be some function of, some parameters, and the strategy of player 2 be a function of some parameters. The overall strategy you care about here is the vector x, which is a vector with two components, player 1 strategies and player 2 strategies. So here you have a vector valued function to represent individuals' equilibrium strategies. Again, there's lots more reasons why you use this. I don't think I have to convince you too much about. It's pretty useful to be considering more than one explanatory variable. If you have gone into social science believing that one explanatory variable is all that matters, you're going to have some issues really fast. So that's really why we use these things and what the use is. Now, I didn't erase all this other math because I want to mention a couple more properties of these functions of more than one variable. The first is continuity. Continuity was a pretty important property. Without continuity, you can't differentiate at all points, and so on. What's continuity here? Well, it turns out continuity here is the exact same thing continuity was back with one component of a function and one variable, which is you can draw that function without lifting your pencil, right? Or the limit of the function from both directions, it goes to the same point, which exists. Same exact meaning. It's a continuous function. It doesn't jump, basically, intuitively. Except that must now be true for every component of f along every variable. So if I take the function, given some other x's, and I vary one of the x's, the function can't jump. That must be true for every component, for every value of x, for all the other x's. Right? So let's go through it again quickly. So if I have some function that's like this, so here's f1, x, y, and z. Well, when is f continuous? F is continuous if for every x and y, and for both f1 and f2, the function does not jump when I draw it as I vary z. right? The limit of the function of each component of the function as I move z towards some point c goes to the same point which exists, and that must be true for all points x and y, and must also be true for the variables x and y, right? So the fact that the function goes to a common point in the limit was the definition of continuity. So for instance, here's f1, I'm going to pick arbitrarily f1 and some arbitrary points x and y. Then my function in z better look like this. So no jumps. If I pick a different point x, y, maybe it looks like that, right? But it still must be continuous. It must have no jumps. It must be true for every point x and y. And then I also have to do the same thing for x and for y for each point of the other two variables. So you might imagine this could get really time-consuming to check this. Usually it's pretty apparent if things are continuous from looking at the actual functional form. But the point is, conceptually, all you're saying when you say a multivariable function, even a vector-valued function, is continuous, is that it's continuous in every single variable, in every single way, for every single component. It's just really continuous. So continuity, though, means the exact same thing as before. There's no difference. Linearity, another important definition, is also the exact same as before. So if this function is linear, and we'll just do a scalar valued function for the moment, then if we have x plus y, I'll just do this all at the same time, a and b are constants, then this is equal to f of x plus f of y. So this is the standard definition of linearity. Note this is different from an affine function, which adds some other value there. Now note, we spent a lot of time dealing with linear functions of vectors in the previous part of the class. This is the topic of linear algebra. You can represent any linear function, as we did previously, by a matrix. So here all we're saying is that a matrix times a scalar times a vector plus this is going to equal the scalar times ax plus scalar y by, which we know from the previous, all the properties of vectors and matrices we talked about in the previous part of the class, linear algebra. So this tells us nothing new, but we see that we've already dealt a lot sort of with effectively multivariable functions in the previous part of the class, because every single thing we did with matrices was effectively dealing with a multivariable function. So there you go. We've also actually dealt with quadratic functions a little bit of multivariables. When we talked about quadratic forms, we call this was a quadratic form, which gives you a quadratic function in more than one variable. So we've even seen that before a little bit too. All we're doing is generalizing that to more complicated functions that aren't just quadratic or linear, functions like, say, x1 to the x2. Right? That's neither quadratic nor linear, but again, it's just one of many possible functions of more than one variable, which come up pretty often. Okay. So that pretty much covers almost all the topics here. I'll also have to sort of discuss a little more when we see these things. So I'm going to give an example from the book, which is a really common one you see a lot in political science literature, which is utility of a politician or a party or whatever that cares about two things. One, a policy enacted in office, we call it X, and two, some amount of goodies, right? We call it G. Here, goodies can be something like discrete, like say cabinet share, portfolio share, or it could be something like actual bribes or money. Whatever. We typically assume that these politicians or parties or candidates have what we call quasi-linear utility. Here it consists of one term that you've seen before, which is a quadratic loss function. Here, z is your ideal point. It's the point you most want. X is the policy enacted. The closer x gets to z, the greater this term gets. By greater, you mean going closer and closer to 0, because the term is always negative. Looks like an inverted parabola, recall. I'm going to add to it some linear value of the goodies, g. Here, g is just some well, it's just added to it linearly, which is why I call it quasi-linear utility. Okay. Now we can ask ourselves, what this means. Well, first of all, we can note that this is a way of representing multiple preferences over multiple things, x and g, in a single function, a single utility function, and therefore this falls into the category of multivariable functions. So again, these are very common. You see this all the time, which is why this particular lecture happens separated from the other stuff in this chapter. Okay. So there you go. Now, what more can we do with this? Well, I can introduce the concept of a level set. A level set is the set at which the function is level, constant. You also see the prefix iso, isoquant, isotherm refer to any area of constancy, any region of constancy of the function. In the case of a utility function in particular, you more commonly see the phrase indifference curve. It means the same thing. It means the point at which the utility is constant. Because the way utility theory works, if you have a constant utility, you're indifferent to all points that give you a constant utility. We call it an indifference curve because the utility curve along which you're indifferent to all possible outcomes that lie on that curve. So these are all similar concepts that let us look at how utility, let us understand how utility changes with the variables. So first we could say set g equal to 0. What's a constant utility curve? Well, in one dimension, there's an x. What are the x's that are constant? So if you're, sorry, let me make this 0, not x. Here's a 0 in the middle of the thing. Well, what's the x's that are constant? Well, if your z is over here, say, then you're indifferent between any points that are equidistant from z, say here and here. So you're indifferent. So your indifference curve in this case for constant z is just 2 points. Now what's my curve? If you had, say, 2 dimensions, and say you had no g, but you had a 2-dimensional x and a 2-dimensional z, so z was some point in 2 dimensions, then the difference curve would be a point equidistant from z again, but here this would be a circle. Yeah, not a great circle, but that's supposed to be a circle. If you care about one dimension more than the other one, you might have an oval. Anyway, but going back to this example here, what happens now if you have g and x both varying? Well, again, it's in 2 dimensions now. Right, here's the dimension for x, here's the dimension for g. You try to map out when you have constant utility. Well, we're not going to do the whole thing right now because it depends somewhat, but the basic point is it's all points at which u is constant. So if you wanted to say have constant u equal to 1/2, what does that curve look like? Well, how do we get 1/2? Well, one possibility is if g is a half, that's up here, say, and x equals to z. So if this were z down here, then if x equals z and g equals a half, you get a half. I should probably have left room there. What if g equals 1? Well, if g equals 1, how would you get that? Well, if g equals 1, then you would need this quantity to equal -1/2. So in other words, x is a distance of 1/2 from a z. So you can move it over, say, here. So you could be fine here or also up here. And so on. And in fact, you can sketch this out sort of more broadly. You know, this will end up looking something like that. The further you get away from z, the more goodies you need to counteract the loss in policy you get. And this, therefore, dictates a trade-off between policy and goodies. Goodies substitute for policy in the sense that the more goodies you have, the more you're okay with the policy being further from your ideal point. Vice versa, if you have a policy closer to your ideal point, you need fewer goodies to make you happy. That's it. So again, this is just one of many, many, many examples in which we have more than one variable for a function. that come up in political science and all the social sciences, so it's very important to be comfortable with using more than one variable. But as I hope you've seen in this particular module, there's really not much difference. Everything is exactly the same as before. It's just more bookkeeping, more bookkeeping. A little more care must be taken to try to keep track of all the variables and the components and such, much like it was in linear algebra. But fundamentally, we're doing nothing different than we did dealing with functions of one dimension. Thank you very much.